Good morning. Greetings from me and my colleagues from India as well as Malaysia. Today's talk I am concentrating on the virtual tests for studies in impact engineering and prototype testing. The motivation came from somehow bringing in the complex laboratory tests to a virtual test model so that it can be shared, distributed, and pursued both for learning as well as for prototype testing. The talk is outlined in terms of these 11 topics, and we'll briefly touch on some of them because of the constraint of time, as you know. And there are 46 slides, so we'll quickly go through some of them. And those of you who are interested to discuss with me can see me personally as soon as my talk is over. The talk about impact loads, then virtual testing, virtual tests for studies in impact engineering, dynamic load modeling methods, analytical methods, experimental investigations of impact load response structures, virtual hammer drop test, virtual Charpy test, then research significance, conclusions and recommendations, of course, the references. Now, the impact load is a complex phenomenon, as all of you know. When two bodies collide, there is an impact. Probably it all started with the apple falling and hitting Newton's head, and immediately he reasoned it out. What is it that is causing the headache? Is it the impact, or is it the apple, or is it the incidence? So then he started reasoning out and gave the laws of motion, which are the basis for modern day Newtonian mechanics. Out of which, the second law of motion, which says unbalanced force is equal to mass times acceleration, gives the clue to understand the impact. Essentially, it amounts to saying that I can interpret the impact also as an impulse momentum relationship. The second law says force is mass times acceleration, which can also be written as mdv dt. That also can be written as md square as dt square. If you combine the first with the third, you can also say f dt is mdv. F dt is the so-called impulse, and that is the change in momentum, the right-hand side change in momentum. It is essentially, if you plot the force transmitted during impact, it will be sudden, as shown in that figure, as you see there, and acts for a short time of contact between the bodies. There are several possibilities of this, about which we will see shortly, and the impulse momentum relationship can be used to develop many of the numerical methods as well as analytical methods that are used for studying impact problems. These include collision problems, crash problems, or missile problems, and various kinds of protective structures that are being developed and designed in these days. Then, as I told you, impact load is defined as high intensity load that is transmitted to a target object within a short duration. Thus, it might cause fracture of structures instantaneously. Therefore, the ability to simulate the impact event by analytical or finite element method can greatly reduce the cost, time, besides improving the versatility. The virtual tests are modern test methods that are being developed in recent times using computational techniques in simulation and modeling. After the reliability of virtual tests, it should be verified, of course, based on the data that we have or in existing details that we have from the so-called impact event. And these are preferred because they have low cost, high efficiency, low risk, process controllability, fewer restrictions, and iterative procedures with necessary improvements. Hence, virtual tests can be used to replicate prototype testing efficiently. Once you develop the so-called virtual test, you can replicate prototype irrespective of shape, size, material properties, and environments. So virtual testing and virtual labs are increasingly being used in test analysis and design of industrial structures and components. Of course, in India and USA also have launched these virtual lab programs. India has a very large program of virtual labs from all branches of science and engineering. So, with that motivation, we started looking at the possibility of developing virtual tests for impact engineering. So, since the computational technology has progressed rapidly, the reliability of these virtual tests is also getting largely improved. Therefore, virtual test has high potential in precisely investigating the impact response of industrial structures or components expeditiously and repetitively. However, the reliability of the modeling methods should be verified by experimental results and analytical results, which wherever possible before it can be used extensively in evaluating impact response of design. Now, as I told you, in the dynamic modeling method, we have analytical methods, and of course, of late we have the finite element simulation method. We use ABAQUS simulation for our studies. The analytical methods can be used for very simple structures like beams, plates, and shells of regular shape, size, and material properties. And the analytical methods, if you look at the possibility of application, there are several approaches, basically based on Newton's second law of motion. FDT is MdV. Either you can use FDT data, if you have, or MdV data to fit into the response equation that you have to solve if you want to use analytical methods. And of course, they are very difficult to analyze, not easy to comprehend, and also not easy to compute. So to that extent, analytical methods can be used only to verify the results on standard structures while developing the virtual tests. But then subsequently, virtual tests can be used for making it more versatile for various kinds of shapes, sizes, and material properties and environments. So that is the reason why we have limited possibilities of analytical methods for regular structures like planar beams or plates or shells. But for complicated structures, either you use the finite element simulation. They also cannot be tested using the standard laboratory tests because of shape, size, and material properties limitations. Okay, so these are some of the earlier work that have been carried out, include in the process. Typically, the equations look like it is for a beam. Similarly, you have for a plate. Similarly, you have for a shell. See, the right-hand side is because the load acts for a short time, it can be imposed either as an external load or as a change in velocity. So there are two methods that are essentially used in this particular process. One is the simple, straightforward analytical method, that is the so-called using model analysis, or using the energy method. Of course, some of the expressions that are used are already classical, are available in classical mechanics. You can test it for simply supported beams, or fixed beams, or a cantilever kind of beam, for essentially developing the analytical solutions. These are essentially used only for verifying the experimental test that we carry it out so that the test can be calibrated using the standard solutions. They use beam functions, which are given in standard textbooks for beams and so on and so forth. So for different boundary conditions, we can use the different so-called beam functions to satisfy the geometric as well as the so-called full force boundary conditions of the given structure. Okay? And the model analysis, as I told you, uses the second aspect, that is change in velocity, as the right-hand side, and develops the solution, while the so-called energy method uses the left-hand side, the FDT, as the input and tries to develop the solution. We develop these solutions ourselves, and some of these solutions are presented in these complicated equations. You can see even for a simple planar beam, the solution becomes so complicated, really speaking. So for different boundary conditions, different kind of solutions are evolved and presented there. Now, in summary, the analytical methods, model analysis, for an impact of a hammer on the structure, the solutions can be worked out in this following fashion as presented there. And they can be evaluated using any of the simple computational techniques. Now, the right-hand side shows the soak lab test that is commonly used, that is the hammer drop test. Now, we apply the solutions to the hammer drop test for verification purposes. Okay? So, if we do the analytical method in hammer drop test, this is the kind of solution that you get for various kinds of heights of hammer. Like if this is the hammer that okay, that is the hammer drop test, that is the hammer there, and it has limited capabilities in terms of the width that is allowed for the specimen and the height that is allowed for the hammer drop. So, with the limitations, we obtain the model analysis as well as energy method for a specific type of problem. This is the beam that is being tested here, and we replicate the solutions using the analytical method, which is the model analysis and the energy method. If you do it, this is how the solutions come out. The analytical solutions are shown here, model analysis as well as this is for a particular height of drop. Okay, different heights of drops, we have different kind of solutions, both model analysis as well as the energy method. They are almost the same whether you use this model analysis method or for the energy method. All right. Now, generally the so-called impact test in the laboratory is carried out using either a split Hopkinson pressure test or Charpy impact test or Izod impact test or hammer drop test, out of which, of course, this is Charpy impact test is used for fracture mechanics, and hammer drop test is used mostly for many of the structural evaluations. Now, virtual hammer drop test using FEM method has been simulated using ABAQUS 6.8 version, basically. Now, hammer drop test can be used to examine the dynamic response of structural members with different types of materials and impact loads. For instance, steel, concrete, timber, composite, layered plates, etc. can be tested. In this presentation, the response of reinforced concrete beams were tested using hammer drop test because they are very so-called non-homogeneous in that sense. You also have embedded reinforcements to be represented by the ABAQUS test. You want to see the versatility of the simulation procedure to be applied for various kinds of beams. For steel, for concrete, and timber, and composites, these have been tested thoroughly, and we have established a correlation between the analytical solutions as well as the hammer drop test. Now, this is the hammer drop test, and the whole simulation, we simulated the falling hammer, we simulated the support. Actually, this is the actual lab test. This is the hammer, and there is a pointer here which applies the load at a point as an impact, and the whole thing has been simulated using ABAQUS, including the movement of the body here, that is the slave, and the master here, that is the beam. Now, it can be used also for multi-body dynamics, that means when two bodies are colliding. But we kept one body static, another body falling, and the simulation has been carried out to replicate the hammer drop test completely using the ABAQUS. So, there are three methods of you can apply for applying the velocity, that is the impact. Either you use the normal height and let gravity act on it and hammer fall on the beam. This is the beam, and that is the hammer, and that is where the point which transmits the impact onto the beam. In the second method, you can use a normal height, but you can give a velocity. It doesn't have to be a gravity. And the third method, you can put the hammer wherever you like and give whatever velocity you want to give in the ABAQUS simulation. So, with these various kinds of approaches for giving the impact, you can replicate literally most of the incidents that are taking place in collision. So, let's see some of the algorithms that are used. In this, there are several contact algorithms. In some cases, the body penetrates the second one. That is the slave, and that is the master. Now, the impact can create a position such that the slave penetrates into the master, or the slave reflects back because of the hardness that is there, creating fracture here in this particular structure. So several possibilities can be created using the contact set algorithm, general contact interaction algorithm. So if the body penetrates, you can show. If the body pierces through, suppose a bullet goes through a structure, that also can be simulated. Literally, you can see the bullet penetrating through the structure. Or if suppose it gets reflected back, such as in the hammer drop test, that also can be reflected. So for that, we used essentially, we tested all these for the hammer drop test, and we found that penalty contact algorithm is the best suited, which allows the reflection back. That means after a little bit of time, TL, the hammer bounces back. It doesn't penetrate. So with this kind of a contact algorithm, and of course the details of the ABAQUS algorithm has been shown here. The various specimens have been tested of various spans, widths, depths, etc., to see how the correlation works out. See, this is the actual simulation, ABAQUS simulation. That is the actual hammer falling. Hammer is falling here, and the simulation is here. That is how the ABAQUS simulation comes. So, if you increase the momentum, the hammer cracks this beam also. So even that has been simulated here. The crack propagation that has taken place because of the impact that has created on the beam. So some of the results of this are shown in this particular slide. You can see this simply supported beam. This is the results of impact forces, how to calculate impact forces using the ABAQUS simulation. This is the impact force plotted as a function of the height of hammer and the weight of the hammer for various specimens, and these are compared with the analytical results. So the analytical results, both energy method as well as the model analysis, are shown in comparison with the ABAQUS simulation that has been carried out. So you can see this, most of the times they are almost the same except for some shift in the time parameters because of some choice of parameters that you have to choose in the ABAQUS simulation. Now these are the comparison between maximum displacements. You can see literally all the methods give identical kind of, almost identical kind of results for various span sizes, beam sizes, and depth sizes, etc. And crack propagation also has been noted. This is how the center of the beam looks like when it has cracked for various kinds of sizes of beams, and the test results are summarized in terms of when it is cracked for a simply supported beam or a fixed beam. The crack lengths have been measured, and they also show the kind of results which are almost the same. And we can bring out a kind of a result showing the critical impact force that initiates the cracks or critical momentum that initiates the cracks. Now, similarly, another test is normally carried out using, for the impact, is the virtual Charpy test, which uses a rotating hammer to hit the surface. And the Charpy test looks like this. This is the rotating hammer. This is where the specimen is put. And the rotating hammer has been simulated by ABAQUS. And of course, the simulation and the original are shown here. This is the original Charpy test. This is simulation. And some of the parameters that are used for the simulation are taken from the actual test. And you will see that the ABAQUS simulation uses Johnson-Cook plasticity model to predict the failure. So this is the simulation. You can use the velocity gravity to apply the velocity and impact here, or you can choose a rotational velocity. You can simulate a given rotational velocity to hit the sample. Here you can test a simply supported kind of a beam of a small size just for the testing, and the general interaction algorithm is used in this particular case, and these are the test results, the mesh sizes that have been used. This is how the simulation takes place. You see here the actual hammer, and that is the actual simulation. See, this is the sample, and this is the actual simulated version. This is a sample, this is actual simulated version. Okay, then you can use this. You see, so that's how the simulated version looks like. So the Charpy test literally shows the kind of impact that it generates. You can measure the failure, the cracks, everything that is there, and some of these models are shown in the subsequent. Okay, some of the results. Absorbed energy. Charpy test measures the absorbed energy, and when it has cracked, when it has not cracked. And this is how the physical models look like. And this is how the simulated model looks like. Exactly, you can simulate the failure here, the failure here. Almost all the samples show identically similar results using the simulation. So the deformation has been calculated, and the virtual hammer drop test also, as well, virtual Charpy test also is kind of simulated using the ABAQUS. So the advantage of this is now you can use them after calibrating it to a wide variety of other objects. Like for instance here, the maximum width I can test is 25 centimeters. Suppose I want to test a structure which is wider than that, I can't do using in the lab. Now with the simulated test, having calibrated it, I can apply it for any size, shape using the ABAQUS simulation. And not only that, in the lab you have limitations of height of the hammer, you have limitations of velocity of the hammer, whereas once you simulate it, now you can use it for any high velocity or any high impact that you want to generate to see whether, let's say, a vehicle crashes or a bullet passes through a particular kiosk or whatever it is kind of situation. You can literally predict what could be the possibility when the two bodies collide. So that's the advantage of this kind of a simulation that has carried out. Then, of course, as the developed virtual impact tests are capable to evaluate the impact response of beams, these models can be used further for modeling the dynamic response of other structural members such as slabs, columns, and industrial components due to impact load. Since the developed model can be used to model the crack response of two colliding bodies, it can be further used to study the colliding body incidents such as developing bulletproof structures, impact on pipes, carrying fluid, buildings, collision of vehicles, crash tests, etc. And of course, these are the references. And thank you very much. If you have any questions, you see me, I will definitely be more than happy to answer it. Thank you very much.
Thank you.